Huh? Today is the 12th of October, 2017. So we have to go back and talk about light. And people had been observing light for a very long time. Isaac Newton is the one who gave us the spectrum of visible light. He was a real freak, seriously. Like, he got the spectrum of visible light by sticking his fingers in his eyes till he saw colors. He did all kinds of weird stuff alone in his room. We don't want to know. He was kind of crazy. But, you know, genius, crazy person. It's a fine line. The EM spectrum includes the visible light that we see that you're using right now. It also includes forms of light that you can't see. So there are things like ultraviolet light. Okay, and we're gonna have an ultraviolet light source in here next week. X-rays. If you've had an X-ray, they take beams of electromagnetic radiation. Easy for me to say. In the non-visible portion of the spectrum, they shoot them at your body, and your body blocks out some of them, producing an image on the X-ray film of your internal structures. That's pretty cool, because they go through the less dense tissues of your skin and your muscle, and they don't go through the more dense tissues of your bone. Nice. Microwaves. We use these to cook food. We use these to transmit cell phone signals. Gamma rays. Gamma rays are bad. You don't want to be exposed to gamma rays. I just heard an account on the radio. I think he just died. Either the only one known to have in the first place, or the last one living known to have, a man who was present. Well, I mean, here, I'll set this up for you, and you can see how much of it you catch just from context. He was a Japanese businessman who in 1945 was traveling away from his home on business at Mitsubishi headquarters in Hiroshima in the first week of August in 1945. He was walking down a country road, and he saw a plane drop an object, and he knew it was a bomb. They'd been at war for years. And he laid face down in a ditch, and he later recounted, before he heard anything, seeing a blast of light and a great wind. And that would have been the gamma radiation passing over his body. Now, he survived mostly because he was late for work that day. Mitsubishi headquarters was leveled. So after he survives the blast there in Hiroshima, he sort of gathers his stuff and he heads home for Nagasaki. He survived both blasts. He was in Hiroshima the day it was bombed. He was in Nagasaki the day it was bombed. Massive exposure to gamma radiation. Amazingly enough, he lived into his 90s, which is shocking because gamma radiation penetrates. So we said X-rays will penetrate your soft tissues, but not your bone. Gamma radiation will penetrate all of you, and it will go right through your cells, and it will rip through your DNA. And it will strip electrons off of the water molecules that are adjacent to your DNA, and then it tends to cause pretty heavy-duty mutations, many of which often, I mean, we all know, because you all had biology, mutations can be harmful, beneficial, or neither. They can be neutral. When you're exposed to that kind of gamma radiation, you tend to have so many of them that something bad is going to happen. Most of the people who survived that kind of exposure died of some sort of cancer. That's also part of the EM spectrum. Okay, well, here's the thing about the EM spectrum. By the early 20th century, certainly late 19th century, we knew that light was a wave. You can all draw a wave. Go ahead. I know you want to. There's a wave. Yay! It's a transverse wave, not a longitudinal wave. You might remember that in physical science. We talked about that in physics. It is a transverse wave. And we can measure stuff about waves. Well, that's very convenient. We can measure things about light. Three of the things that we commonly measure with waves: wavelength, frequency, and wave speed. And those things are all related by a very simple equation. We talk about the speed of light as c. You might recognize that from the equation that Einstein proposed, which has nothing to do with the atom, but a few people, well, I don't think anybody this year, because I told you in advance, that often ends up in the atomic theory presentation. So we can describe that relationship as speed is equal to wavelength, that's lambda times frequency. Okay? That's a terrible lambda. Those are Greek letters. That's convenient because we're going to actually calculate a few things. So let's do a couple sample calculations. And here's the nice thing about light. And actually, all forms of electromagnetic radiation travel at the same speed. And the speed of light is 3 times 10 to the 8th meters per second. That's pretty fast. So just to give you a sense of scale, 30 meters per second is about the speed that you might drive up and down Route 7 at. So that's 3 times 10 to the 1st. We're talking about 3 times 10 to the 8th. Pretty darn quick. The sun's, what, 93 million miles away? I'm so ashamed of myself that I don't know that in metric. And it takes light from the sun 8 seconds to get here. Pretty fast. So let's say that we have a piece of electromagnetic radiation. We know how fast it travels because C, I'm going to move this around because it's a good practice when you're doing any kind of equation to list your variables. C equals that. Let's say that it has a wavelength of 4 times 10 to the, what would that be? Nano, negative 9th, negative 4 times 10 to the negative 11th meters. That's a teeny little wave. That's a teeny little wavelength. Remember that wavelength is the distance from either the center point back to the center point. Boy, that's a terrible wave. So that, or from one crest to the next crest, or one trough to the next trough. You have to go through an entire wave cycle. So if we've got a wavelength with a lambda of 4 times 10 to the negative 11th meters and a velocity of 3 times 10 to the 8th meters per second, can you solve for its frequency? Of course we can. Don't be silly, Moser. Let's do that. Words of caution on solving algebraic equations. Many of you I know will go on to physics. Oh, for the love of God, rearrange the thing first. Do not stick numbers in and then solve it. I will beat you with a physics stick next year. This year, I'll just growl at you. No, I might beat you with a chemistry stick. We'll see. So we are solving, of course, for frequency. And this is a pretty easy solve because, let me move this over so we can see it all. C divided by lambda gives us frequency. Okay, easy peasy. This is where, hey, remember how I said you really needed to master that whole working with exponents thing? Okay, 3 times 10 to the 8th divided by meters per second divided by 4 times 10 to the negative 11th meters per second. If you don't have a calculator, you probably would want one. Let's move that up, pause. Okay, so we get 3 divided by 4 times 10 to the 8 minus negative 11. 0.75 times 10 to the 19th. We're going to fix the scientific notation, don't you worry. What are the units here? Meters per second divided by meters. Be careful. Not seconds. The meters cancel. The meters cancel. It's a weird one. They're 1 over seconds because frequency is given in cycles per second. Not a big deal, but you should know it. Okay, so moving that, we're going out this way. So that would be, let me shrink this, 7.5 times 10 to the 18th cycles per second. Yeah. That's a lot of cycles per second. And when we say cycles, if we imagine this wave as a wave in the ocean passing a post, like a pier, that is the number of cycles, the number of troughs or the number of crests that will pass that pier in 1 second. That's a lot of waves. That's because you have a tiny little wavelength. So what's the relationship between frequency and wavelength? Inverse or direct? Inverse, when one gets larger, the other gets smaller. Direct, when one gets larger, the other gets larger. What do you think? Well, let's imagine something. Here's this wave. Here's my little post in the ocean. Let's imagine that this has a wavelength, we'll say we're starting from here, trough or crest to crest. If I change that to a wavelength like this, will more waves pass that point per second or fewer? More. Many, many more. So, when frequency goes up, or I'm sorry, when wavelength goes up, frequency goes down, and vice versa. The longer the wave, the less frequently it will pass a point. What does this have to do with the atom, Moser, for the love of Pete? Sorry. I know it seems like a sidebar. I promise you it's not. I promise you it's not. Okay, well, we knew that light behaved as a wave because we measured things about light. We measured its wave speed, we measured its frequency, we measured its wavelength. We didn't totally get how they were all connected immediately, but, you know, whoops, nope, already did that. But we knew that it was a wave. Now here is something interesting. 1913, Niels Bohr, the Danish physicist, proposed electron orbits with varying energy levels. Well, this explained the emission spectrum of hydrogen. Huh? What's that? Well, let me show you something. This is hydrogen's emission line spectra. People had known for a long time that, anyway, so you put the hydrogen in a low pressure tube, you run current through it, it glows, you take that glowing pink light and you run it through a prism, and what you see is that there are actually, I should do this in a color that shows up, 1, 2, 3, 4, 5 distinct bands of light at very distinct frequencies. All moving with the same velocity, but very different frequencies. It's not a continuous spectrum of light. If you run just plain old white light through a prism, you get all of that. But you take hydrogen and you do that, you only get these little bits. Huh, that's odd. That's kind of what you're seeing here. I've added some different elements to, yes, plain old, simple old alcohol gel hand sanitizer. It's a relatively safe, flammable. There have been some pretty serious chemistry lab accidents doing this demo using liquid alcohols like methanol. You don't ever want to do that, and if you ever see a prof or anybody lighting up methanol in the open, you should get out of the room. But the alcohol gel hand sanitizer is a pretty safe bet. It's pretty containable. I mean, heck, we couldn't even get a few of them to light. So it had been known that these different elements give off different colors. That's what you're seeing there. I had barium chloride in one, lithium chloride in another, strontium chloride in another. What else did I have in there? I forget. Potassium chloride, I think. And so all of those things glow with a different color. And if we were to put them in a low pressure tube and run current through them, we would get a spectrum. Okay, cool. So what Bohr proposes is that those orbits that Rutherford talked about, he says, well, yeah, but I think that there are varying energy levels and that the electrons are locked onto those energy levels. I think they're locked there. He doesn't really change the Rutherford model, except that he adds to it. By saying there are these energy levels, they're locked into those energy levels, and that's why they don't just get sucked into the nucleus, because they're like locked into these tracks. What he also says is imagine that these are rungs in a ladder. They can only exist on one rung or the next. You can't put your foot in between the rungs and stand on it. You're standing on air. You can't do that. And what he says is it takes energy. If you add energy to an atom, you can kick an electron up an energy level. So you can take this electron and move it up. Well, I won't invite you to stand on your chairs just yet. We'll do that in a little bit. But he also says that when that electron falls back down an energy level, it's going to give that energy back. Guess what form? So he says it takes energy to kick it up an energy level, and then when it falls back, it gives that energy back out into the environment. Guess what form he claims it gives it back in? Light. Light. Oh, interesting. Interesting. So with that, I'm going to pass out a lab packet. We're going to talk about it a little bit. This is a very quick lab. You'll probably get this done in 35 minutes. So we'll go over the break, but you can take your break at 4. And then we're going to continue this conversation because we're going to look at the specific flame colors of a variety of elements. I'm going to stop the video here and we'll pick back up.